3, 2, 1, go live. Okay, we are now live. Hi everyone, welcome to the 5th Sherpa free lesson. This one is going to be on math sequences, held by Devon here. So yeah, I'm going to hand it straight over to Devon. Kick us off.
Perfect. Thank you. Thank you. So today I was wanting to talk about sequences. Now, the reason I like sequences is because one of the things that I really enjoyed when studying, for example, GCSE maths was sequences. Oftentimes, I would just write my own sequences and try and figure out, if there is, say, a given sequence. Let's just make up a sequence. For example, 1, 2, 4. Now, if let's say we have the sequence 1, 2, 4. Now, you could ask yourself, what is the next term in the sequence? And I always used to think, is there only one possible term? Well, the answer is no. There isn't just one possible term because, well, we don't know what this sequence is. This sequence could be the sequence +1 here, and then we've got +2 here. So maybe it carries on +3, and maybe the next term is 7. Maybe. Right? Or maybe that's not the sequence at all. Maybe the sequence has been multiplying by 2 every time. So if we're multiplying by 2 every time, maybe the next term in the sequence is 8. Right, so we have a little bit of a problem here. So what you realize is there's different types of sequences. And this is what I find so fun, is that if you give someone, say, just some numbers to start off a sequence, you don't actually know what the next number in the sequence is going to be until you know what type of sequence it is. And then another question that popped in my head is if I get any random set of numbers, let's say I just pick 590 different numbers and put them one after another. Now, are they the terms of some sequence? Can I find a sequence for which those would be the first 590 terms? Now, of course, these are questions beyond something I can figure out, right? Way beyond something I can figure out, because the questions I'm asking are like ginormous. It's impossible to figure out. But we can kind of make this a little bit more basic and start from the beginning with GCSE sequences. And one of the things I want to really go on today is looking at quadratic sequences. So we're going to start off with arithmetic sequences, right? And then we're going to move on to quadratic sequences. And I'll explain exactly what these are and what it is that I want to present to you today. Because I believe the current method shown in terms of how to solve quadratic sequences is just not efficient. I have found something a lot simpler and easier to understand, and I want to show you the way in which it works. And the reason I want to show you the way in which it works is because I believe there's no point in me just teaching you something and say stick this in a formula and solve it. It's much easier if you understand what's going on, so I think that's what we're going to do. So let's start off with some arithmetic sequences. So this may be a sequence, for example, like 1, 3, 5, 7, 9. Now, you may be able to tell me the next term. You may say to me, I see. All right, we're adding 1 each time. I mean, 2 each time, sorry. So you say add 2, add 2, add 2, add 2. And if we do that again, well, the next term in the sequence is going to be 11. But remember that problem I told you about earlier? Well, maybe that this is the start of some numbers to a different sequence. So we can never know what what the next number in the sequence is unless we're told the type of sequence it is. And in the case of arithmetic sequences, the rules are that every time you add the same amount. So if we're adding 2 here, we're going to add 2 again, and add 2 again, and add 2 again. So it's actually, because I've told you what type of sequence it is, if I have an arithmetic sequence, let's say I say the first 2 numbers are 5 and then 8. The nature of the arithmetic sequence means that you know all the rest of the terms in the sequence because the sequence works in the same way each time. So if this is add 3, then because it's an arithmetic sequence, the next thing that you must do is add 3, because you have to add the same number each time. That is why it's called an arithmetic sequence. That's one way or one kind of category of sequences, and they're relatively simple. Now, remember I said that we can't figure out what a sequence is based on the first few numbers in the sequence. Well, there's a solution. This is the solution, and there's a solution to this which is shown at GCSE. Again, they don't explain why this is necessarily useful, but I believe, or at least in my head, I say it's because if I use this technique, I can actually identify a sequence, and then I can have a unique way of expressing each individual sequence specifically. So I'll explain what I mean by that. So let's just take out 1, 3, 5, 7, and 9. Now, you may or may not have heard of the nth term rule. So the nth term rule is something which helps you to identify what a sequence is, find out any term in that sequence almost instantly, and if I give you a number in that sequence, you can tell me which number term that is. So, for example, let's firstly start off with me explaining what I mean by which term it is. Well, this term, which is 1, which is the first term, we're going to call it the first term. This is going to be the second term. This is the third term. This is the fourth term. This is the fifth term. All very logical, right? All makes a bunch of sense. But we want to be able to relate the place that a number is in the sequence to what the number actually is itself. So I'll tell you what the nth term is for this sequence to begin with, and we'll see how it matches up. So the nth term here is 2n minus 1. Right, now what does this mean? Well, if I'm going to say the nth term, right, I'm going to write it as an equation. The nth term equals 2n minus 1. What does that mean for my sequence? Well, if I was to replace n with 1, what would happen to this equation? Let's see. So it would be the 1, and then instead of saying, 1 and then the 1th term, that doesn't make any sense. The first term is what we're going to say, of course, right? So we're going to say the first term equals, and replacing the n with 1, because of course n is 1, we have 2 times 1 minus 1, which is just 2 minus 1, which is 1. Okay, well, what if n equals 2? Let's see what happens. If n is 2, then we're going to say the second term is equal to 2, and then replacing n with 2 here. So it's going to be 2 times 2 minus 1, which is 4 minus 1, which is 3. Now what you notice is I've just said the first term is 1, and the second term is 3. And what you see is this is the same as this sequence here. So actually what's happened is this nth term rule here is a way to uniquely identify this sequence. Now, of course, this isn't a proof that this is the right nth term. I've just shown you that 2 of the values work. Now, I can make up a different formula, and the first 2 values will be 1 and 3, but maybe the sequence goes off differently. But you can believe me for now. Right, I'll show you how this works after. But this is how we're going to start. So this is what an nth term is, and what happens is when you replace any number for n, you can find out whatever the number of n is, what that term in the sequence actually is. So if I said, okay, a question was, well, I know what the first, second, third, fourth, and fifth term is, but I want to know what the 100th term is. There's some reason as to why I want to know the 100th term. Not a problem. What I do is I replace n with 100. So then, based on this formula, the 100th term is 2 times 100 minus 1, which is 200 minus 1, which is 199. And all of a sudden, I actually know what the 100th term is. And that's really useful. So that's a reason for using the nth term. Equally though, what if I said to you, I know that the term 387 is in the sequence, but I don't know what term it is. Well, notice what we can do here. We can say, well, the nth term equals 2n minus 1, right? Now, this nth term is 387. That's what we're trying to find out. So we can say to ourselves, 2n minus 1 equals 387. So then 2n equals 388. So then if we divide both sides by 2, we get n equals 194. What does that mean? Well, that means that it's the 194th term in the sequence. So this is another reason why having this nth term rule is so useful. It's this solution to trying to identify exactly what the sequence is. So if you remember, we started off with the sequences 1, 2, 4, and then it could have been either 7 as the next number or 8 as the next number. That sequence right there, or both of those sequences right there, fit into other categories of sequences, not arithmetic sequences. So I'll just show you those again. So 1, 2, 4, and then either we can have 7 or we can have 8, depending on what the type of sequence is. So one type of sequence could be +1, +2, and then +3. That's a quadratic type of sequence. And then this is times 2, times 2, and times 2. Again, that's a different type of sequence, which actually you don't need to worry about just yet for GCSE. But we'll go into it anyways, because I think that it's very interesting and not too difficult. Right. So let's carry on with this arithmetic sequence business and think about how we find out the nth term of an arithmetic sequence. So what we do, I'll show you the method, and then I may even show you how it works. So we have an arithmetic sequence like that. And the first term, let's say, is 5. The second term is 9. And then we have 13. And then we have 17. Now, there's a rule I like to use, which is, firstly, we're going to think about what the term before the 5 would be. So this 5 better be the first term, and this better be the second term, etc. Right, so we're going to think about what the 0th term is. I like to call it the 0th term, right? So let's think about what's going on here. Well, from 5 to 9, we're adding 4. From 9 to 13, we're adding 4. So logically speaking, something, which was a 0th term, plus 4 is 5. So I hope you can see that the 0th term must be 1, right? So this must be 1 because we're adding 4 each time. So we have this 1, so we're going to keep this 1. Cool. And then we're going to say add, and then what's this difference every time? What's a common difference? We call this plus 4 the common difference. Well, this is the common difference. So we're going to have plus 4 in brackets, which is our common difference, times n. And that is your nth term. So what is our nth term? Let's think about this. So it's 1 plus, and then plus 4 times n. So 1 plus 4n, or 4n plus 1, however you want to write it. So we can say the nth term of this sequence is 4n plus 1. And we can try it out. Let's try it out just for the first term. Right? So if we say n equals 1, so then the first term is 4 times 1, add 1, which is 4 add 1, which is 5. And that checks out over here. Perfect. So this is how we're going to figure out the nth term. Now, how does this work? You can say, how does this work? How does this method come to be correct? Well, I'll show you. So let's take a very general sequence. Now, this is a little bit more complicated. This is something which I expect, if you're starting your A-levels, you may understand kind of some of the notation here. So let's think about arithmetic sequences, but let's label things very generally. So U1 is going to refer to the first term. And similarly, UN is going to refer to the nth term. So the number, which is in the subscript of this U, is going to be the number of the term. So a sequence, an arithmetic sequence in general, right? Let's talk about arithmetic sequence in general, is going to be U1, U2, U3, U4, ... Well, all I've written there is that we're going to have the first term first, then the second term, then the third term, the fourth term. Great. So that's just how sequences work, right? They just come one after another. Now, how are we going to figure out what the nth term is? Well, let's think about how arithmetic sequences work. Well, what happens is we add or subtract a common number here. So we're going to say we add this d for difference, and we do that every single time, right? So let's think about what we know about the term-to-term rule, right? So if we say U1 add d equals U2, okay, that's pretty good. Now let's think about what UN is. Well, UN is here, let's say. So, okay, so if we're trying to find out what UN is in terms of U1, right? So let's think about it. UN in terms of U1, right? So if it's U2, it's U1 plus D. If it's U3, right, it's going to be U1 plus D and then plus D again. So it's U1 plus 2D. Because notice we're doing plus D and then we're doing plus D again to go from U1 to U3. And then notice if we want to go to U4, we've got to add D again. So it'd be U1 plus 3D equals U4. Right, so can we notice a little pattern here? Right, can we notice a little pattern here? Well, the pattern I see is that U1 plus, and then let's think about UN right here. So if we have the number 2 here, we have 1D. If we have the number 3 here, we have 2D. If we have the number 4 here, we have 3D. So it always seems to be 1 less than this number here. So if we have UN here, it's going to be n minus 1 times D. So it's going to be whatever this number is, take away 1, and that number of D's. Because look at this here. So U1 plus 1D equals U2. So there's 2 here, 1 here, 3 here, 2 here, 4 here, and 3 here. So that makes a bunch of sense. So this is actually something we can find out. But then I like to take it a step further and say, well, what about U0? Well, let's try and think about what U0 is. Well, U0 plus D equals U1, as we can see from this here. U0 plus D equals U1. Right, so let's replace this expression for U1 into this formula over here. So if U1 is equal to U0 plus D, then U0 plus D plus n minus 1 times D equals UN. Or in other words, U0 plus, sorry, let me just undo that, plus, and then if you've got n minus 1D plus 1D, right, so I'll write that out, n minus 1 plus 1 times D equals UN. We have U0 plus, and then notice that n minus 1 plus 1 is just n, so we have plus n D equals UN. And compare that to what I told you to do. Well, what do I actually mean by U1 plus ND? What that actually means is the 0th term, because notice this number here tells you what term in the sequence you're on, plus, and then n times D. So n is just n, right? That n is just going to stay, and D is this common difference. right? And so it's the common difference times n, right? And that equals the nth term. Now let's look at what I told us to do here. What I said, let's look at the 0th term here, right? And then I said, what's the common difference? So if you notice, this is u0, and then this common difference here, this plus 4 is the d times the n. So we had u0 plus n, dn, and I said this was equal to the nth term, which is un. So u0 plus dn equals un. And here you see we have the exact same equation, right? So that's how it works. Now, of course, you don't need to worry about how it works too much, right? If you can understand some bits of it and not other bits of it, that's completely fine. But it's just there for you to really, if you want to, if you just want to know how it works, you can run through this again. You can rewatch this and try and follow it more again and again. If it's just a nice insight, you can just listen to this once and leave it there. But it's just so it's not just like you're being lectured and said, do this, do this, do this. That's how you do it, and then you never get told why it works. Because to me, there's no point in that, right? I'm always curious about how things work. So I hope that if that interests you, that was helpful. Now, we're going to move on to something more complicated here. We're going to move on to quadratic sequences. Now, I'm going to show you how these work. These look deceptively simple, but to find the nth term for them is actually pretty difficult. But I'll teach you, or I'll show you the method that you're usually taught in school, and then I'll show you my kind of different method for this, and with all the reasoning behind how it works. So quadratic sequences are as such. So for example, an example of a quadratic sequence is 0, 2, 6, and then 12, and then 20, and 30, and 42, dot, dot, dot. And again, the funky thing with quadratic sequences is you actually only need three terms, to be able to tell you the rest of the sequence. Remember, with arithmetic sequences, I said you just need 2 terms in the sequence to know which arithmetic sequence it is. With quadratic sequences, there's an added layer of difficulty, so you need to know the first 3 terms or any 3 terms in the quadratic sequence, and you can work backwards to find out what that quadratic sequence is. But of course, with the added complexity, we need to know more terms. So how does it work, you may ask? Well, this is how it works. So we think, what do we do? What do we add from 0 to 2? Well, we add 2. What about 2 to 6? Well, we add 4. What about 6 to 12? We add 6, and so on. And what we notice is there's some sort of a weird pattern, right? So we call this the first difference. So we're going to label this the first difference, like that. Okay, so why have I labeled that the first difference? Well, because there's a second difference. Right? We're going to have another line of differences. Right? How is this going to work then? Well, we have this plus 2 and this plus 4. What's the difference? Well, plus 2. Plus 4 and plus 6, what's the difference? Well, it's plus 2. And then plus 2 again, and then plus 2 again, and then plus 2 again. Okay, well, we start to see that this second difference is all the same. Now, let's compare this to an arithmetic sequence. So if we had an arithmetic sequence here, 1, 3, 5, 7, notice if we do the first differences here, straight away, we have a common first difference. So clearly something's a little bit different here. Something's a little bit more complicated. We're having to go one step deeper into the sequence to find the common difference. It's almost like if you're trying to find the pattern in the sequence, but you're having to dig one step further, one difference deeper down to figure out where it is that you can find the pattern within the sequence. Right. So let's have a think about what's going on here. Well, the first way in which you're taught how to do this is you take this second difference and you divide it by 2. Right, so you divide it by 2. And the number you're going to get here, well, the second difference is 2. The common difference is 2. So you get 2 over 2, and that's 1. Well, what do you do with the number 1? What's the use of number 1? Well, the use of the number 1 is this goes in front of 1n squared. Right, so it goes in front of this n squared here. So you have 1n squared. Okay, so then you say, well, how is this useful? Well, this is how it's useful. So we take our original sequence, 0, 2, 6, 12, 20, dot, dot, dot. We compare it to the sequence n squared. Right, let's compare it to the sequence n squared. Now, let's think, what is a sequence n squared? Right, we're going to do this on the next page. Right, what is a sequence n squared? Well, let's say the nth term is n squared. That's what we're saying. So what does this mean? What it means, if we're doing n equals 1 to figure out the first term, then the first term is 1 squared. But notice if we do the second term, it's going to be n equals 2. So the second term is 2 squared. Okay, so what is the sequence? Well, the sequence is going to be 1 squared, 2 squared, 3 squared, etc. Or in other words, 1, 4, 9, 16, 25, etc. Right, and then if we try and write that out here, 1, 4, 9, 16, and 25, and then we try to look at what the difference is between these two sequences. Okay, Well, why do we just take one away from the other? Why do we just take one away from the other? Right, so let's say our nth term is 0, 2, 6, 12, and 20. The n squared sequence is 1, 4, 9, 16, and 25. So if we do a simple addition, a simple subtraction, right, we can subtract on the left side of this equal sign, and so the nth term, which is what we're looking for, minus n squared, because we're doing it like some column subtraction as if it was with numbers. I know it's strange, but follow me here. And we're going to see what happens. We have minus 1, minus 2, minus 3, minus 4, minus 5. Okay, so what have I been able to figure out here? Well, I've been able to figure out some new sequence. And this new sequence, minus 1, minus 2, minus 3, minus 4, minus 5. Well, let's think what is this sequence? Minus 1, minus 2, minus 3, minus 4, minus 5. Well, this is a sequence minus n. Right, why is it that? Let's find out. So the nth term is minus n, right? So if n equals 1, the first term is minus 1. That checks out, okay. N equals 2, so the second term is minus 2. Yep, it is. Perfect. So the nth term is minus n. So then we can say the nth term minus n squared equals minus n, because that's minus n on the right-hand side. So then if we try to rearrange to get the nth term, well, the nth term is, and we add n squared to both sides, n squared minus n. Okay, so that's a little bit more complicated. Why is it a bit more complicated? We've got this squared term, and that's what makes it a quadratic sequence, right? That's what makes it a quadratic sequence, right? So let's move on, and let me explain a little bit about how it works. So that's kind of how they are going to teach you how to solve it, but I've got a better way. I've got a better way. I claim to have a better way. So let's look at the quadratic sequence in a slightly different way. And we're going to do it in a similar way to how we looked at the arithmetic sequence. So as usual, we have the first term. We're going to call U1. Hope you're used to that notation by now. And then we have U2, U3, U4, and so on. So that just means the first term, the second term, the third term, and the fourth term. Right. Now, the general form of a quadratic sequence is as follows. So the quadratic sequence, and you may recognize this, and you may think, I see why it's called a quadratic sequence, right? This is because the quadratic sequence has this form. Its nth term is equal to an squared plus bn plus c, where a, b, and c are just some numbers. They can b and c could be 0, a cannot be 0, because then you'd have 0n squared, which is just 0. And then you just have an arithmetic sequence, because it'd just be bn plus c. That's an arithmetic sequence. So a cannot be 0, so let's just write that down. A cannot be 0. B and c can be 0, no problem. And this is the form of a quadratic sequence. It looks a lot like a quadratic equation, right? It looks a lot like the thing that you solve with the quadratic formula. Well, it's almost the same thing. It's just we're talking about sequence here. So this thing has popped up somewhere else. So let's think about what this nth term is really telling me. Now let me just rub this out to give us a little bit of space, right? So we know that a is not supposed to be equal to 0. I'll write that on the side so we don't forget. Right, let's think about what U1 is. Well, what is U1? Well, U1 is the first term. Okay, how else can I describe the first term? It's a tricky question. Well, we can use this general nth term rule. So the nth term is an squared plus bn plus c. And I realize we don't know what a or b are, but there's no problem with that. Let's think about what the first term is. Well, to figure out what the first term is, we need to replace it with n equals 1. So then the first term is a times 1 squared plus b times 1 plus c. Well, why is it that? Well, it's because we replaced the n with 1. Right? So then the first term is equal to this a times 1 squared, which is 1, plus b times 1, which is b, plus c. Now, why have I gone about figuring this out? Well, the reason I've gone about figuring this out, notice what we had in the last equation. Well, in this last method, we had a little bit of, I would say it's a little bit confusing. It could be a little bit confusing, especially with this column subtraction. It's not exactly clear why and how this works. And I don't believe in kind of going through something and not knowing how it works and just accepting it. There's no use in that. So let's have a look at what I did here, however. So we had this nth term equals n squared minus n. So really speaking, if the nth term here was an squared plus bn plus c, I just figured out that a itself, this number a must have been 1, b must have been minus 1, and c must have been 0. You might say, how does that work? Well, let's think about it. If this was the values, then the nth term would be, well, a is 1, so 1n squared is just n squared. And then if we add bn, so we add and then b is -1. So instead of adding bn, we're just going to be taking away 1n. So just take away n. And then c is 0, so plus 0 is not going to make a difference. So at the end term is n squared minus n. But really, if we'd found out what a, b, and c are, we could have just figured out what the nth term was, right? Rather than having to do all these different calculations. So that's what I believe in. So let's try and do that. Let's try and figure out what a, b, and c are. Well, I know for starters, whatever my first term is equal to a plus b plus c. Okay, that's interesting. Now, let's go a step further. Right, let's go a step further. Let's figure out what the second term is. Well, if n equals 2, then the second term is a times 2 squared plus b times 2 plus c. So the second term is 4a plus 2b plus c. Okay, so what I've realized is the c is still there. This 4a, we've got 4a and 2b instead of just 1a and 1b. Okay, so how can I use that information? Well, let's go to the next page. So I'm going to rewrite some of the stuff on the last page. We've got u1, u2, u3, dot, dot, dot. That's our sequence. We've established that a quadratic sequence is of the form nth term equals an squared plus bn plus c, where a is not equal to 0. Okay. And then we said that the first term is a plus b plus c, if you remember. And the second term is 4a plus 2b plus c. And then we're going to do the third term, right? We're going to look at the third term for a second, right? So if n equals 3, then the third term, remember we're placing this into this equation up here for the nth term, right? We're trying to find out some equations with a, b, and c and see what we can do with them. So the third term itself would be a times 3 squared plus b times 3 plus c, which is 9a plus 3b plus c. And now you may be thinking, what can we do with these terms? What's the use of knowing this? Right? So what's the use of knowing this? Well, I'll show you. So we're trying to find out what a, b, and c are. So we can take this like simultaneous equations, albeit a little bit more tricky. Now, let's think about what we can do. If we figure out what the difference is between the second term and the first term, right? So the second term minus the first term. That's what we can call like the first difference between the terms. And let's think about what this tells us. Well, what this tells us is 4a plus 2b plus c minus a plus b plus c. All I've done is I've replaced the second and first term with things that we understand. So all I'm talking about here is this difference here, whatever this difference is here. That's what I'm figuring out here. So if I want to say that d there is equal to second term minus first term, which is equal to this minus this, which is equal to, and I'll do this quickly, 3a plus b. That's it. So the first difference in that sequence, and remember the differences are changing. So if we go back to our original quadratic sequence, the differences are changing. So we've got plus 2, then plus 4, then plus 6. I'm talking about this plus 2 here, or whatever it may be. It may start plus 4, it might start plus 8, it may start minus 10. It doesn't matter what it is. But that difference is equal to 3a plus b. That's useful to know. Another thing that we know, even though I've already written it, I'll write it again, is that the first term, which we better express as u1, just for simplicity, and because, well, in general, in maths, if we can write something in really shorthand, we will, is equal to a plus b plus c. That's useful. And then the final thing I'm going to do is kind of just to show you how that rule about this first term, which is a, being equal to the second difference over 2, I want to show you how that works. So let's just have a think. So u1, u2, u3, right? Now, instead of saying u1, u2, and u3, we're going to replace it. We're going to say we've got a plus b plus c, which is our first term. We've got 4a plus 2b plus c, which is our second term. And then we've got 9a plus 3b plus c, which is our third term. Now, if we're doing the first differences, let's take a look at what would happen. So the first difference is, when we take a look at this, we have 3a plus b here. And then the first difference here is going to be 5a plus b. Okay, now what's the second difference going to be? Well, the second difference is equal to this 5a plus b minus this 3a plus b. And if we do that over that, we get 2a. Okay, that's interesting. We've got 2a as being the second difference. So if the second difference equals 2a, then a equals the second difference divided by 2. So that's how it works. You may have thought, how does that work? Well, this is how it works. Again, I know this is pretty complicated, and I'm going over it pretty fast. So if you need to go back and rewind and rewatch this, by all means, go for it. If you want to try it out, write it in your notebook, try and solve this for yourself. Again, go ahead and do that. It can be a pretty good exercise. It's pretty fun to try and work out these things. and especially that, I mean, I don't need this like a few weeks ago. I found this out by just pure curiosity. And let's see how this works. So I believe if with those three equations, and I'll write down those three equations again that I've shown you, is that firstly the first term, so u1 is equal to a plus b plus c. The second one I had was that the first difference between the first two terms is 3a plus b. That's useful. And then finally, the a equals the second difference over 2. I think if you figure out a sequence in this way, if you try to find the nth term of a quadratic sequence in this way, your life becomes a lot easier. So let's take the original quadratic sequence and let's see how it works. So you saw that the quadratic sequence n squared minus n, right, because we figured out the method that you're usually taught, is 0 to 6, 12, 20, dot, dot, dot. Now, notice with the method that I'm using, we only even need to consider 3 terms. So we're only going to consider the terms 0, 2, and 6. Let's say 0, 2, and 6. And then the first thing we're going to do is calculate a here. So if we calculate a, we're going to get, well, the first difference is we have to do is 2 and 4. Notice 0 plus 2 is 2 and 2 plus 4 is 6. So that's the first difference. And the second difference here is 2 because 2 plus 2 is 4. So we know straight away what a is. So a equals the second difference, which is 2, divided by 2, which is 1. Okay, we know what a is. Cool. Now we're going to figure out what this second rule is telling us. So the second rule here that I've devised is the second term minus the first term is equal to 3a plus b. So what does that mean? That means this is the second term, this is the first term. So 2 minus 0 equals 3, and then we know what a is. We just figured out a is 1, so 3 times 1 plus b. So 2 equals 3 plus b. So then if we take away 3 from both sides, minus 1 equals b. So now I know b equals minus 1, right? We can write that down. Cool. And then we've got this final rule, which says the first term is equal to a plus b plus c. So this first term is 0. So 0 equals, and then a is 1. We figured that out. Then plus b, which we figured out was minus 1. And then plus c. Okay, so 1 minus 1 is 0. So 0 equals 0 plus c. So c must be 0. And then if we figure out what we've said here, we said a equals 1, b equals minus 1, c equals 0. And remember that general form that we said before about the nth term of a quadratic sequence? We said it's the nth term is equal to an squared plus bn plus c. Well, a is 1, we said. Now b is minus 1 and c is 0. And if we implement this into our equation, well, we get the nth term equals 1 times n squared plus minus 1 times n plus 0, which if we simplify is just n squared minus n, which is our correct answer. So this is my alternative method. Now, this does save a lot of working on more complicated quadratic sequences. So actually this quadratic sequence 0, 2, 6, 12, 20 is one of the simpler ones to calculate using the other method. But notice the method I've shown you here is one which works with even more complicated quadratic sequences. For example, there are quadratic sequences which look a little like 5n squared plus 7n minus 8. And maybe you'll be expected to be able to figure out that that is the nth term. But using the method I've just shown, trying to derive this nth term will be very, very easy and a lot easier. And hopefully you can see via these explanations why it is the case that the rules I've given you work. And if they don't make sense straight away, again, no problem at all. They're fun to look at. Try and find them out yourselves. You can rewatch this video, of course, and have lots of fun with it. So I will leave it there in terms of these sequences. Of course, I know you'll open up to a Q&A, so I'll leave it to you.
Okay, yeah, I'm back. That was an excellent lesson, Devon. I learned a lot of stuff about that, about nth terms there. We do have a couple of questions, so let me just bring them up now. So the first one actually came through. I'm just going to pop back in your notes because I was making a note of where it came through. Where was it? I think it was on this page here on arithmetic sequences. And it is, would it be the same rule to find the 1000th term?
Would there be the same rule to find the 1000th term? Absolutely. So let's say we're trying to find the 1000th term. Well, how are we going to denote the 1000th term? Well, if the first term is u1 and the nth term is un, well, the 1000th term is u1000. And if we've got this nth term rule here, right, which is un equals the 0th term plus nd. And notice if we go back a slide, right, we had an actual arithmetic sequence, which we found this for. We found that the nth term was 4n plus 1. So let's work with that sequence, right? So let's try and find the thousandth term of this sequence. Well, the nth term is 4n plus 1. So if we replace this n with 1,000, right, then the 1,000th term is 4 times 1,000 plus 1. Or in other words, 4,000 plus 1, better known as 4,001. So the rules do apply absolutely. So this is talking about a general arithmetic sequence. So in a general sense, if we were to replace this n with 1,000 here, it would be u0, and then replace this n here with 1,000. So it would be u0 plus 1,000d. In other words, in words, it would be the 0th term plus 1,000 times the common difference.
Brilliant. I've actually got a question on that. I'm going to assume the answer is no, but does the rule ever change, or if the sequence, if the rule is the rule, it's never going to
So
change? I'm assuming.
yeah, the rule is it stands for all arithmetic sequences. So if we've got a sequence where we're adding or subtracting the same amount each time, these rules will absolutely stand, right? It's if you have a different type of sequence, like the quadratic sequences we're looking at, then the rules are completely different. But the rules of arithmetic sequences are as follows on the screen.
Okay, cool. And the other question that we've got is specific to you. So, does your way of working out quadratic sequences meet mark scheme criteria for exams?
Absolutely. So one of the misconceptions with GCSE maths and kind of all kind of maths is that you have to follow the specific method. It's a great question, by the way. Specific method of what you're taught in class, and that's absolutely not the case. Most of the time, your teacher says, "Show your working" for your marks. Now, in some cases, the reason why you need to show your working is because you can do the same question on a calculator, and they need to know that you did it and you didn't use a calculator. So, of course, you need to show your working. But when it comes to a question like this, if they see that you've used a method, even if the examiner doesn't understand it, and I would doubt that they would, right, if they saw you use this method, as long as you've got the correct answer, that's all that matters. The only time when you're working actually matters is if you get the end answer wrong, right? So if you get the end answer wrong, the whole idea is they can give you working marks back. Absolutely, it's fine. Don't worry about the mark scheme criteria. And yeah, you can go ahead and use this method just fine.
Okay, brilliant. Yeah, that was the only questions we've got. But if anyone has any further questions, you can leave them in the comments below, and I will relay them on to Devon, and I'll get an answer from him. Same with the YouTube comments as well. If you're looking to get some lessons with Devon, you can check out his Sherpa profile at the link in the description of this YouTube video, and also on the Facebook comments. He's an excellent tutor. I'm sure you've just figured that out given the lesson he's just taught. Brilliant flow, went over everything that you'd need to know. So yeah, I think Devon is a cracking tutor. And also, if you're looking for another tutor, maybe in sciences or English, what you can do is you can head over to sherpa-online.com. You can have a look at tutors yourself, or you can give one of our tutor experts a ring on 01628 337 590. That's it from us for today's free lesson, and we'll see you next week.
Thank you.
Cheers, everyone. Bye.